Here with us, we have Vijay Singh, who is the Executive Director of Business Development at NextEra Energy Resources. Vijay, thank you so much for joining us.
Thank you. Good afternoon, Chairman Huck, fellow commissioners and staff. Thank you for inviting me. And my job today is to present energy storage, and I'll focus on technology and applications. So with that, let me find this clicker. Clearly, it's a publicly traded company, so I threw in a slide on legal disclaimer. The company I represent is NextEra Energy. I work for NextEra Energy Resources in the development group. We are focused on energy storage development. So as a company, NextEra Energy, think of its two businesses. One is Florida Power and Light, serving customers in the state of Florida, and other business being as a wholesale generator serving our customers across the country. And between the two businesses, we have shared platform, engineering and construction, supply chain, and on generation side. So as a company, it's I got over 90 billion in total assets, 60 billion in market cap as of April. So Florida Power and Light, as I said, it serves 4.9 million customers approximately in the state of Florida, 26 gigawatt in operation. And energy resources, I'll call NextEra Energy Resources the wholesale generator as energy resources going forward. It owns 20 gigawatt, serving customers across the country. About 14 gigawatt, I apologize, out of 20 gigawatt is wind. Roughly 70% of our generation portfolio is wind, and rest is solar, nuclear, and gas. So with that, I'll jump into the energy storage executive summary. So if you look at lithium-ion battery prices, I think most of you are familiar with this technology. We use them in electric vehicles. We use them in mobile devices. We use them in laptops, the iPads, and the iPhones. We have seen a dramatic reduction in cost over the last 4 to 10 years. There's a lot of scaling up going on in this sector. Electric vehicles, there's an increased demand of mobile devices, electric vehicles. So what that has done is it has given the scale to the industry, reducing the cost. In addition to cost reduction, there's a lot of innovations going on technology side per se, where the energy density of a battery, which means like the footprint, is improving. So you can pack in twice the energy in the same footprint that you could maybe 4 years ago. Which means you can find a lot of use cases, either substation or connected to distribution feeders and so on. So in addition to economics, footprint also becomes important for utilities and developers. So if you go back to 3 to 4 years ago, the lithium ion is kind of new in stationary storage. It has been used in other devices, but scaling up of lithium ion batteries started, I would say, in PJM. So in PJM has about 270 plus megawatt now, which was supported by Reg D, regular frequency regulation, market design that started several years ago. And since then, now this was special, like Reg D signal was created for storage devices. 15 to 20 minute battery duration worked to serve that particular application. Since those 3 to 4 years ago, applications are now moving towards more longer duration batteries. So demand charge management, you can roughly do it with 2 hours in California, for example. And then you move on to resource adequacy, which is a 4-hour battery product in California and certain other jurisdictions. So we have seen the growth of, I would say, the battery duration as the cost has dropped. Applications are more and more applications are making economic sense. So be it renewable integration or resource adequacy, we see near-term demand to be driven by that. And longer term, I would expect 4 to 8 hour battery systems, providing multiple use cases. It could be T&D enhancements and support, renewable integration, clearly, resource adequacy, peaking services, and so on. So I think we expect the battery cost to go further down, but at the same time, there's a limit to how much it'll go down. We also have to keep in mind the other technologies, and I'll talk about that, that folks are looking at. They're still emerging, more of a pilot. The question is, what could disrupt lithium down the road? So the way we look at that is like an iPhone. Everybody has an iPhone, and this device came about 10 years ago, and people used it for 2 or 3 things: making phone calls, sending emails, and things like those. But over time, more and more apps got developed. So you don't know what you don't know until you actually have the device, and then people found a lot of benefits. And so we look at energy storage the same way. More and more apps are being added to storage. As we deploy, as the cost comes down, people try to understand. They not only understand the technology itself, but the use cases. So that's how we kind of correlate to the development of this technology. Now, this presentation is more or less about batteries, but storage doesn't mean it's battery alone. You got a whole spectrum of technologies that can serve storage needs. On the right side, in the green bubbles, you see a pump hydro, which is a very established technology, has been deployed around the world for several years. You got thermal storage, ice, heated pumps, water heaters, things like those. The sodium sulfur was a technology used last decade before lithium ion came in, produced by NGK from Japan. And then you got yellow bubbles, which is lead acid, and K is compressed air. Now, they're matured, but they could not scale up due to certain limitations, including cost. On the left side of the graph, you'll see a lot of bubbles, a couple of bubbles that I'm trying to show, that some technology that's going through lab testing still. Non-lithium, could be zinc-based, and so on. Still commercial, it's not commercialized on a large scale, but something to keep track of. And right in the middle is a lithium ion, which, as I talked about, is kind of what is the preferred technology for market participants today. So I talked about how electric vehicle industry is driving down the cost for lithium. So the graph on the left this is from Bloomberg New Energy Finance. Way back when, about 7 years ago, in 2010, you'll see a cost at $1,000 a kWh, and now it is expected to be less than 300 a kWh or less going forward. So clearly over 300% reduction in cost. And then you'll see simultaneously, you'll see a growth in electric vehicle demands, the green chart being annual and yellow being the cumulative demand for electric vehicles. So now the graph on the right is, we also compare to other technologies. What has happened? I saw a graph early on. We looked at solar, for example. If you look at this slope, how the cost has come down with increased scale and increased production of panels. Now, batteries, the lithium doesn't have so many data points, but if roughly speaking, the slope is almost there. And this clearly scale in this ecosystem actually drives cost down. So with that said, I just wanted to kind of highlight a couple of terms we use in battery space. When we buy a battery, we are buying energy. There's energy content within the battery. We are buying kilowatt hours or megawatt hours. So usually we define, okay, what's a battery cost? People say $1 per kWh. That's what I'm buying. The other piece is the power, which is rate of discharge of that energy over time, and that's typically driven by the size of the inverter. Right? So the rate at which you release energy is the power. So think of it this way. So if I have a 1 megawatt hour energy battery, if I release 1 megawatt per hour using 1 megawatt inverter, I get 1 megawatt for an hour. Now, if I need to discharge 2 megawatts over 2 hours, I need 2 times 2, 4 megawatt hours of energy and 2 megawatt inverter. So plus round trip efficiency, actually, you need more of it. So in general, energy or energy content of the battery or electric vehicle folks typically talk about energy content in terms of kWh. If you buy a Tesla, that's 70 kWh kind of battery. So just wanted to kind of highlight this terminology for you. Now, the battery in itself is not good enough. You still need system and architecture around it. You need to rack it up. The smallest denominator is a cell. You have seen cells. Actually, let me go to the next picture. On the left, you'll see a pouch cell. Manufacturers make different shapes and sizes. They could be cylindrical cells that you see in Home Depot and Lowe's, typical AAA and AA batteries. You could have prismatic cells. So these cells then need to be scaled up. So they typically put them in a module, and then put all those modules, rack them up. They're like file servers. You rack them all up, and at the top of the shelf is usually a BMS, what we call battery management system. It's like the brain of the whole rack. It monitors the voltage, the amperage, and temperature of the system. And all these racks have their own battery management systems, which really is important to know that makes it very, the architecture is very modular. So if one rack goes down, rest of the system will continue to work. So availability in these systems are very high. So once you take those battery racks, you containerize them. You can put them in a container, or depending on the use case, you can put them in a building. Now, the voltage coming out of the battery is DC. You need to convert it to AC, so you need an inverter. And then you have a step-up transformer. Because the voltage levels are different for different batteries, I would say 500 to 600, maybe 1,000 volt. It needs to be stepped up to a grid level. So that's how the battery will discharge. And on the way back from when it's charged from the grid, or a solar resource or a wind resource, the AC needs to be converted to DC. So you need a bidirectional inverter, which is a kind of new technology. A lot of folks have used in the solar world a unidirectional inverter system, but a bidirectional inverter, there's a lot going on here as well. How can we improve the voltages? How can we make it off-the-shelf item? So the cost on the inverter side also needs to come down, as well as balance the plant to make the whole system cost effective. So here's I threw in a picture of one of our systems. This is in Illinois, 20 megawatt system, just to kind of show you what it looks like. So you got 8 containers on the back side, 2.5 megawatt each worth of batteries in them. And within each container, you'll have, fire suppression system, you'll have air conditioning, you'll have control systems. And the 4 boxes, the containers you see in front, these are inverters, 5 megawatt each. Then you have step-up transformer, and the voltage gets stepped up to 34 kV, and then 138 in this case before it goes to the grid. Typically, that's how the system works. So now one thing I do want to point out is not just the battery alone, it's also the integration. Right? What kind of battery do you pick for a different use case? The battery chemistries are different, so you have to be very careful of the chemistry that gets picked. The type of inverter you pick, how do you containerize batteries? Should they be in a container, on a building? What are the permitting requirements, the local jurisdiction? What are the fire suppression systems? So when we go for permitting with the local zoning authorities, we have to talk about all those issues. And how do these different hardware and control systems talk with each other and to the grid? Equally important, so it's more than just the batteries. Now, I'll move beyond technology to applications and use cases, and I think it has been talked about by different panels here. It serves the whole spectrum of grid applications, from generation, transmission, distribution to the customer side, because it not only acts as a generation, it also acts as a load. So I have colored these boxes, kind of say different applications require different duration. So for example, you got a first box under generation says renewable ramping. Now a utility on an island, if they have a lot of solar penetration, if the cloud cover comes in, the frequency drops. So one utility wanted the frequency to arrest the frequency drop and actually control it on the way down. And when the solar cloud goes away, frequency moves up. So they wanted to make sure it has a controlled ramp up and ramp down of frequency. So I don't need a 4-hour battery for that. So it's what I call a short duration batteries, or Reg D in PJM is 15 to 30 minutes battery. Or you can pick a blue box, a resource adequacy. That's in California. 4-hour batteries qualifies for capacity products. I'm sure you've all heard of Aliso Canyon. There was a gas leak in California, and the commission actually accelerated the procurement of battery systems to provide resource adequacies in those areas. And energy storage came in within 4 to 6 months. So that was a particular problem in California as a unique problem. Was solved by energy storage in that case. 2 years ago, nobody would have forecasted that kind of problem in the solution. So it's kind of coming back to the apps, right, that we are adding. So think of these as the apps on the iPhone. And if you take those applications and kind of map them across technologies, it's not just the battery. The other technologies can do the same functions. As you move to the left, which is a short duration, you got supercapacitors that they give you a power boost to perform certain functions in the voltage regulation and things like those. Grid stability, and to the right is pump hydro. They can be discharged over a number of days if you have enough water behind the dam. So it depends on the application and use case. So I'll talk about a few use cases here. which I think are important to understand. So what we did was we took some public data that was available. We pulled in power plants, peakers that were running 10% capacity factor or less than 10% capacity factor, and we drew some graphs around it. So what you'll see is we wanted to kind of know how often do they get called, these peakers, and when they do get called, how often do they run? So this chart is essentially we have mapped all the peakers that ran 10% capacity factor or less. So you'll see that 95% of all the calls were for 8 hours or less in New York ISO, and roughly the same theme. So at least 92% of the times they ran 8 hours or less. So here's the question. Is there a use case for storage? Are there congested areas, congested load pockets, transmission congested areas? They're permitting difficult. Maybe there's no gas. These are old diesel plants about to retire. Can we come in with 4 to 8 hour storage product? So it may not work in every jurisdiction, but there are places where it could work. So that's something industry is looking at. That's what resource adequacy is in California. So I just wanted to highlight this. What are you calling it? Peaking resource. You can call it capacity resource. Or it doesn't have to be 4 hours. It could be 2 hours. Super peak could be something else. Second is the duck curve. I'm sure everybody has seen this. So this load profile is net of renewables, net of solar and wind. Essentially, this is the load profile that needs to be served by other resources. So as you see, there's a lot of penetration of solar. It's going from 2013 all the way to 20. More and more solar comes in, it depresses that profile. When the sun goes down and the load is still there in the evening, our load is ramping up, all of a sudden you got this big ramping need. Unless you build new peakers, this is California jurisdiction here. So unless you're building new peakers, you got some issues. And then the head of the duck here is, after the peak, still there's a slow ramp down. So what California is looking at is what you call flexible ramping product. When storage comes in, it charges itself off peak after midnight, provides a morning ramp service, and at the belly of the duck that you see, actually prices are clearing negative in California a lot of times. Battery charges itself and is ready to provide the ramping in the evening hours. Right? So storage has dual use case to it. It can provide 2 ramping products on the same day if you have 4 to 8 hour solution, 4 to 8 hour product. So that's kind of another product, again, very unique to California at this time. The question is, what other jurisdictions will this duck land in, right? Given where the solar prices are? And a lot of people talked about here, solar in Ohio or other places. So that's something to keep in mind. Storage is kind of one tool in the toolbox. It's not the end all or be all of all the problems. So this is another product, since I talked about solar, is solar plus storage. So industry is looking at a DC connected solar and storage now. You can have AC connected too, but by having DC connected, you can clip the solar that was otherwise not being used because of the way the solar systems are designed. You can clip that and actually move it to where the load is in the evening. So not only are you saving the solar energy, you are actually moving it and better aligning the solar resources to the load profile. And by the way, while the storage is there, it can also perform other functions, the voltage and grid stability and so on, frequency regulation included. So that's another product that industry is looking at, both behind the meter as well as in front of the meter. So just let me wrap it up. It's probably my second last slide. The whole lot of applications, we talked about renewable integration, but renewable integration is one of the applications. It could be T&D support, T&D enhancements. It could be peaking service, resource adequacy. It could be, you could site it at a customer site at critical load, provide power quality. You could have it on distribution feeders that is having problem because of excessive solar, so on and so forth. It could act as a demand response at different markets. So, and just a few projects that we have deployed as of March of this year, about 90 megawatts in different jurisdictions, providing a whole range of services from frequency regulation, response, demand response, as well as DCM or demand charge management. So, and we are developing a bunch of solutions for our customers depending on the unique problems in different jurisdictions. So that's kind of my last slide, and I'll open it up for questions. And let's keep focus on technology and applications. I'll be happy to answer any questions you have.
Thank you very much, Mr. Singh. We will go ahead and actually ask Mr. Singh some questions because you have to depart, I believe.
Yes.
So let me open up the dais to any questions. Mr. Conway?
Mr. Singh, the use cases that have been the most productive for you or most feasible, the most frequent for you, which ones would you say they are? And I was looking at your slide 24, the applications, the circle of applications. Are those the types of use cases that you look at? And if so, which ones are the ones that you find the most useful?
I would say they're all useful. It depends on the problem. So we have, as I said, in the last 3 to 4 years, this whole industry has evolved from short duration systems. So a lot of our systems are short duration ancillary products, ancillary services to the grid. But over time, we are providing demand charge management services. And you can also aggregate these resources to provide DR, demand response. So we are doing that. I can probably talk about Florida Power and Light. We have some systems there as well at the end of the feeder, providing support. We have peak shaving system as well. And as the battery costs are dropping, we are developing solutions for our customers that are around resource adequacy or T&D support as well. So now, I haven't shown those projects because this is as of March this year, but there are several more projects that are being developed, not just by us, but others as well.
If you had to estimate which of the different applications generated the most, produced the most installations, the most megawatt hours of storage, which use or which application would you say?
Right, so in PJM, we have 50 megawatts. So PJM is, I would say as an industry, most of the projects, the number of megawatts are in PJM. But very soon now, if you look at megawatt hours, the duration, as I said, has moved now in California. California is a much larger market now in terms of megawatt hour or the amount of energy or the batteries you need to deploy.
Okay, thank you. Commissioner Friedman.
Quick question. Thank you for your presentation. You allude to there being consumer application relative to storage. Do you see certain parts of the conversation this morning revolved around the proliferation of DER and its impact on the electric grid in terms of having to accommodate or integrate as opposed to simply accommodate. Do you see a proliferation in a residential application based on storage technology that would actually enable someone to stay off the grid and thereby avoid the implication associated with the DER on the grid?
Well, there are certain, California, you probably know Southern Cal Edison is seeing thousands of residential rooftops coming. Are they completely off the grid? I don't think so. I don't want to go in that area of policy making and so on. But we are seeing more and more behind the meter solar coming at municipality levels, at residential and commercial as well as the cost drops. And then, as I said, if you add storage to it, you can actually amplify the number of use cases that now you can do. You can form it up. You can offer as a capacity resource. You can be on a distribution feeder and provide voltage support and things like those, which solar on itself may not be able to do. So,
yeah, I would assume with grid parity, as it relates to solar, there would be an impetus for further development in the storage capacity associated with a behind-the-meter application.
Right. And different utilities are looking at different ways. In Puerto Rico, they asked for that storage has to be attached to solar because an island. Right? So as I talked about cloud cover goes off, and then there's a certain drop in frequency. They don't want that. So they wanted to make sure every solar asset at the time should be attached with a battery to provide those functions.
Okay, very good. Commissioner Trumbull.
Just had a question. You mentioned that there's longer duration applications, especially moving into 2018 to 2021. What is longer? Can you give me an idea? Is that more than 8 hours? What are you thinking?
I'm thinking 8 at this time. But if batteries get really cheap, we'll see. Again, battery still needs to be charged up. It cannot be infinite source of fuel. Okay? So technically, you can say it needs 12 hours to charge and then 12 hours to discharge. But you can probably take a little less time to charge itself. But so is 12 the limit? Yeah, you cannot go more than 12 anyway per day. Maybe a little longer, but it's not pump hydro, right? That is unlimited fuel. Well, not for, at least in terms of storage. If you have enough water behind dam, you can discharge for days. So a battery has its limits in terms of duration. Right? So if it's a duration limited application, I think this could be one of the tools to look at, for sure.
Okay, thank you.
Thanks. Mahila.
Thank you, Vijay. In the morning panels, we were talking about interconnection of distributed energy resources. And I was wondering if you use energy storage synergistically with a distributed energy resource, say storage and solar, the interconnection application that is submitted, is it a combined application, or do you submit an application for solar separately and for the storage separately?
It's different. Usually we apply for interconnection for storage separately. So they look at his solar 100 megawatt and his battery 30 megawatt is really 130 megawatt resources. Typically, that's how it's looked at. So is that a question? Yes. So they get looked differently, and for transmission owners and RTOs, they also model the bidirectional inverters differently than a typical unidirectional inverter. So the models they use are different, I think. So yes, they look differently for now that I know of.
And a related question, when you submit these interconnection applications, do you sort of just give the utility maybe a heads up as to the use case scenario, as to whether it's going to be a control technology or, a frequency regulation, application, that sort of a thing? But you're saying it's going to be addressed separately as solar and storage, yes?
Yeah. So when we file for interconnection, clearly our transmission owners and RTOs know what is the use case, what kind of inverter we are buying. Therefore, they can do the modeling. So yes, they know. We just don't go, and we basically tell these are the applications. Usually, that's the case, including our customers. They also know that.
Okay, very good. Mr. Singh, thank you very much for joining us
Thank you.
today. We really appreciate it. Okay, and we'll continue on with our panel. With us today, we've got Don Harrod, who's the village administrator from Minster, Ohio. We also have Ryan Harty, Environmental Business Development, American Honda Motor Company, Inc., and Roger Wilkens, co-director, Pilot Microgrid Project in Athens, Ohio. Thank you all, gentlemen, for joining us today, and we'll begin with Mr. Harrod.
First of all, I'd like to thank you guys for inviting us down here. And let me tell you a little bit about our project, our energy storage project / solar project. And we got to talk about both of them because they're kind of integrated for us. A little bit about Minster. Minster's in northwest Ohio, about an hour and a half from Columbus, and located in Auglaize County. We are a population of about 2,800 people. We're a full-service community with natural gas, electric, water, wastewater, parks, recreation, police, and fire. About 25 full-time employees and $22 million in annual budget. We are home to 3 major industries. One is Nidec Minster, one is Precision Strip, and we are home to the United States' largest yogurt-producing plant, Dannon Yogurt, which produces about 5 million cups of yogurt a day. We have about 1,400 meters. We use about 115 to 125 kilowatts, a million kilowatts a year. We have a diversified energy portfolio, and we have a reliability statistic of about 99.9% of our time, which we're very proud of. But what I really want to talk to you about is our project. About 3 or 4 years ago, we started on a project to build a solar array. what started out as a solar array and ended up being a solar array with a energy storage system. And I'll get into that a little bit. But our solar array is a 4.2 megawatt solar array, consisting of about 13,600 panels, about 17 acres. Our energy storage system is a 7 megawatt, 3 megawatt hour lithium-ion energy storage system. Both of these systems are connected to our own distribution, our 12470 distribution line. The energy storage system comprised of 3 cartons of batteries and 2 controllers. They are built by S&C Electric and run from the S&C storage management system. LG Chem is the supplier of the lithium-ion batteries that are in the containers, and it is tied directly to PGM for frequency regulation sales. We worked with a couple of developers, American Renewable Energy and an investor, Half Moon Power. This is a public-private partnership in the fact that the village could not do this project on our own. We realized that early on, that we did not have the resources, we did not have the financial well-being to be able to do this project on our own. So we started to look for partnerships and developing a third-party partnership with American Renewable Energy and Half Moon Ventures. Our main goal for the whole project was the development of low-cost and reliable electric to what matters the most, our residents and businesses. We also wanted to continue to diversify our electric portfolio and reduce transmission and generation or capacity costs. Those costs are about 20% of our electrical cost, and we felt it was necessary to start looking at ways to reduce that. We also wanted to create our sustainability and resiliency and continue to improve on our reliability. Why did we do this project? Again, just diversifying our portfolio, reduce our transmission costs, and reliability. How do we make this work? As I said, it's a public-private partnership. We have a lease agreement for the ground the energy storage sits on. We have a power purchase agreement to purchase power from the solar facility. That power purchase agreement allows us to buy all the power that is generated from that solar system. And we have an interconnection agreement for both the solar facility and the energy storage. But most importantly, what made this project work was a term called revenue stacking. And that is the ability to utilize all the assets of that battery to do different functions, but also to generate a revenue or benefits for each party that's involved in that. And I'll get into that a little bit later. Some of the challenges we faced, Senate Bill 301, when we were doing this, working with a developer, getting ready to sign a PPA, Senate Bill 301 was passed, which kind of halted interest in developing solar in the state of Ohio, at least for us. So we had to overcome that. One way we did that overcoming is working with the developer and the investor-owned utility to think outside the box. How else could we attract an investor to invest in our solar project? So we started to look at the energy storage and paired those two together and found an investor that was willing to work on both of those type of projects. We also had to do a lot of education on our council and our community. What was energy storage? What are the benefits? How is it going to help the village of Minster? How is it going to lower our rates? We also had, this should say impatience rather than patience. It took us a long time. We had to cover 3 or 4 years to get this all worked out. And the impatience of council and the impatience of the community, we had to overcome that. They wanted to see things happen really quick, and none of this happened very quickly. It took a while. Some of the benefits, and this is where we get into the revenue stacking at. Through the power purchase agreement, we were able to take the benefits of the lower, below market rate for our solar. Our average price of the solar is our average rest of our portfolio price, so it was a very good rate for us. It's a behind-the-meter resource, so we're able to reduce the amount of money or amount of energy we're purchasing from the open market, and we can use a solar array as a hedge against market volatility. It also provides us with a very predictable electric rate. But one of the things with the energy storage, the benefits of the energy storage system, and what I mean by revenue stacking is that we have bad power quality in the village of Minster. With all the industry that we have, our power quality was not very good. We're going to have to go out and look at putting about $350,000 in reactive compensation equipment. By utilizing the voltage support and the VAR support from the energy storage system, we were able to avoid this cost. We're also able to take the energy from the storage system and reduce our peak, utilize it for peak shaving. It reduced our transmission and capacity charges, and the developer also uses it to sell into PGM's frequency regulation market, the Reg D market. So there's benefits not only for the Village of Minster, but there's also benefits for the developer. And that's what really made this project work, is everybody had a benefit. We utilized that energy storage system, all the assets of it, for benefits for each one of us. We also the energy storage helps integrate the solar into the village's electric grid. And again, as I said, improves our power quality. There's also some community and social benefits. We help diversify our electrical portfolio. Now 32% of the village's energy is supplied by renewables, helps our sustainability goals. We utilize it for an educational tool, field trips for school students. We also developed some classroom activities and an interactive website that the school can use. And it was also good for our businesses. Dan and Nidec Minster have sustainability goals, corporate-wide sustainability goals, and we were able to help them achieve those with this project. How do we know that this system is really working? Well, as I said before, one of our main goals was to be able to reduce capacity and transmission charges. And we've achieved that. We've saved about $140,000 in capacity and transmission savings off of the solar this year, and about $20,000 or $30,000 in capacity and transmission savings off of the energy storage system. We hope that this is going to grow for us and become even a higher dollar amount as we get better and better at predicting when those peaks are and being able to use those peaks shaving. What did we learn from the project? Well, we learned of the project that the model was very successful for us. It works for our community. As I said, we weren't able to do this alone, so we had to look at that private-public partnership. We also learned that revenue stacking is essential to making one of these projects work. I think any energy storage project is essential, that you look at taking all of the benefits that a energy storage system has and being able to develop those benefits. And we also learned a little bit of patience throughout the whole program as well. What would we do different? Right now, I'm not sure we would do anything really differently. The model works for us. We are actually going to utilize that model for a second phase, another 4.2 megawatts of solar and another 7 megawatts of energy storage to put on our own distribution system behind the meter. We also are looking at a third phase, which is a 19 megawatt energy storage system that would basically allow us to move into a microgrid capability. And that's the village's ultimate goal, is to be able to be self-sufficient for X amount of time. And we've also started to develop some community solar projects off of this. We've had interest from the community to develop some community projects with this. So it's really taken off. It's really snowballed from what it started out as just a solar system into an energy storage system, into greater things for the Village of Minster. So thank you.
Don, thank you very much. In our usual format, we hear from all the panelists and then we ask questions. So I hope that's okay with the trio. Up next is Ryan Harty. Ryan.
Great. Good afternoon, Chairman Huck and commissioners and staff of the Public Utilities Commission. Thank you very much for the opportunity to speak with you today. My name is Ryan Harty. I'm manager of environmental business development at American Honda Motor Company. It's a lot of fun to have been invited to this. I started my career living in Columbus, Ohio, and working at Honda R&D just up the street. And so it's nice to be back here. Let's see here. There we go. For those of you who don't know Honda, we like to make high-quality products at reasonable prices for our customers' needs for mobility, power, and energy. And people think of Honda as a Japanese company, yet we have R&D, manufacturing, and sales right here in the United States. And little known fact, Honda makes a higher percentage of cars in the United States that we sell than any but one other automaker. And we export cars from the US all over the world, from right here in Ohio. And our history of manufacturing in North America started here in central Ohio with a motorcycle plant that started in 1979. And this was followed by the first auto plant in 1982, and all right here. And today we have manufacturing throughout North America, 3 auto plants, an engine plant, and transmission plant right here in central Ohio. So thank you very much. So I'll skip through that. So why am I here? Because I think Honda has a great story to tell to this commission. We're excited about the Power Forward proceedings. It affects Honda, it affects our customers, our suppliers, our dealers, and it will help us to reach our long-term CO2 reduction goals. Honda's working to dramatically reduce our global greenhouse gas emissions footprint, and this will require zero carbon energy sources for our operations and our product use. And zero carbon energy requires energy storage. And so my challenge to the Commission today is to think big and help solve the big problem. So energy storage it directly leads to massive greenhouse gas reduction for transportation and electricity. And this needs a combination of all types of energy storage: flexible demand through energy management, electrochemical energy storage in batteries like Mr. Singh was talking about, chemical storage in the form of hydrogen that was missing from his matrix but is critical to our business, and thermal energy storage and means of energy management, but also means of directing renewable energy to heating and cooling, and mechanical energy storage. Vehicle-to-grid integration and energy storage are key to achieving the Powered Forward goals, and Honda's already working to achieve those goals, and I will share with you some of those details. So Honda recognized early the need to dramatically reduce greenhouse gas emissions. In 2009, we announced a goal of reducing by 50% our greenhouse gas footprint from 2000 levels. And for the world's largest manufacturer of internal combustion engines, this is a massive challenge. It requires more than a 90% reduction in CO2 per unit of sales. This will require us to launch full scale into the adoption of powertrain electrification, adoption of energy efficiency and renewable energy to power our products and operations. And our product roadmap is to apply a high degree of electrification to 2/3 of our automobile product by 2030. So for an automaker, that's right around the corner. This is a revolution in our business. And over the next few years, our entire lineup of products and operations will be affected. Honda's very optimistic about electrification of automobiles. The Honda Clarity series of cars is our first major foray into electrification. And these are extremely well-appointed sedans with Honda Sensing, Android Auto, Apple CarPlay, spacious interior. I say that because that stuff is important. If you want to launch a revolution, you've got to start with the customer, and you got to provide products that they want to buy in order to develop the market. Electric drive provides qualities that people like. It's a smooth, quiet drive with a lot of torque and acceleration, and people enjoy them. When people buy an electric car, they typically don't come back to internal combustion engine vehicle. We launched the hydrogen-fueled Clarity fuel cell sedan in California in December of last year. The vehicle has 366 miles of EPA-certified driving range on a full tank of hydrogen and can be refueled in about 3 minutes. That's why we're very optimistic about a future involving hydrogen. The Clarity Electric will have 89 miles all-electric range and will be on sale next Tuesday in California and Oregon. And the Clarity plug-in will have 42 miles of electric range with a very efficient gasoline engine to provide unlimited driving range. And these vehicles, together with the ones that follow, will become kind of the core of our business. But the purpose of all of this is greenhouse gas reduction. So everybody knows that you don't get greenhouse gas reduction from vehicle electrification unless you get zero carbon fuels into the vehicles. So that's the core challenge for us as society and as citizens in Ohio. So compared to gasoline vehicles, EVs reduce greenhouse gas everywhere. But compared to hybrid vehicles, which are much lower cost, EVs amount to expensive carbon reductions unless renewable energy is used to charge the cars. So we made that the goal. And now how do we do that? The key is to scale up renewable energy along with an energy management framework. This energy management framework needs massive energy storage. This is the role of hydrogen, to provide massive bulk storage of energy and to decouple energy generation from usage. And transportation, at least initially, is a small part of the value chain. Industry needs to get the carbon out of petrochemicals, industrial feedstocks, fertilizers, and to provide zero carbon fuel for long-haul trucking and heavy-duty transportation applications. Hydrogen can do that. Buildings and operations need firm and secure energy flows, which need energy management and storage to firm up. Electrochemical batteries can do that. Electric vehicle charging can then function as a dispatchable load, and matching the second by second and hour-to-hour variation in generation and usage. So let's look at a concrete example. This is an actual load curve in California on March 31st, 2012. In general, in California, we're concerned about the peak. And EVs have the potential to greatly affect that peak. So for reference, 20,000 megawatts is the charging power of about 3 million cars. That's about 15% of the cars on the road in California. And so it'll take a little while to get there, but it should be on the radar of regulators. Bloomberg New Energy Finance is predicting that by 2038, more than half of the cars on the road will be EVs. So that's 20 years. So already in California, there's a whole lot of solar in the daytime, with the smallest net load occurring around noon. And the result of that is that there are severe ramping needs in the morning as solar comes online, and in the afternoon as solar drops off. This is every day on the grid in California. So this was first published in 2013, but California has already exceeded the 2020 curve shown here. That's a lot of solar. And some people say, solar in Ohio? No way. But I would argue that all of Ohio is a better solar resource than Germany. And everybody thinks that Germany is a global leader in solar, which they are. And it's just a matter of policy and adoption procedures to get there. So this is called the duck chart because it looks like a duck. So what can we do? So we take our electric cars and we go out to find some ducks. Electric vehicles are a very flexible load. It's dispatchable from Honda's servers. With knowledge of the customer needs of the car and knowledge of what's going on the electric grid, we can design an algorithm to schedule the customer's charge and help manage the impact of renewable generation on the grid. We can have cars gradually start charging in the morning as the sun comes on and have cars charge during the middle of the day and stop charging when the sun falls off. This is just one of the use cases of controlled charging, or we call V1G, to make a skinny duck. And with V2G, we can make the duck duck. And so we're also demonstrating bidirectional power flow, or V2G, at UC San Diego. And using V2G, we can discharge into the grid to mitigate the evening peak as well. And so this is all important because the electric vehicle is probably the retail customer's first smart grid experience. And since it's our goal to reduce greenhouse gas emissions, we have to figure out how to direct renewable energy into the cars. And it all starts with the customer and the choices they make to buy an electric car and to enroll in a program to help them manage the charging of an electric car. It has to be super simple and easy for the customer to enroll and participate. The system that we have built to manage the V1G takes the customer's desired charging schedule. It aggregates the information with other EV charging and computes the best schedule for each car, and then bids the charging demand and supply, which is the ability to stop charging for some duration, into the California ISO markets. We start and stop the vehicle charging over a cellular network from our servers. We can also react to real-time market by charging when prices are lower than the day-ahead market and not charging when prices are higher. And this saves the utility money in real dollars. We can also schedule charging according to data from renewable energy generators and react to utility demand response programs. So customer enrollment and participation is key, and that's a difficult part. Without them, we don't have anything. And all of this has real effect of generating some savings and money for the customer and reducing the impact of EVs on the grid. So the next step is to apply this to homes. So a car is actually a smaller greenhouse gas footprint than a customer's home. And together, transportation and residential energy use are about 44% of US greenhouse gas emissions. So if we really want to make an impact, we have to also adopt technologies to address those loads as well. And so first, start with renewable energy for electricity. Then apply renewable electricity to cars. Then apply technologies to reduce the heating and cooling loads, or sorry, the heating loads from heat and hot water at the house by directing renewable electricity into those. And together, when we stack up that, we can achieve a zero net carbon living and transportation. We built a demonstration home at UC Davis in California in order to show these technologies and this capability. And to our knowledge, this is the first zero net energy home, including the energy use of transportation. Well, we did it in conjunction with Pacific Gas and Electric. We take demand response signals from PG&E in order to stop pulling power from the grid. If they need power, we give them power. All of the energy flows at the house, from the solar to the car, from the stationary battery to the car, from the car and back again, is on a DC microgrid at the house in order to minimize the impact of transfers of electricity. We're also publishing all the data. There's 270 channels of data at hondasmarthome.com for people to use and look at and do research on. When we started this project, there was no data out there, so we're making all the data available for usage. For our own facilities, we're starting to look at these as well. So this is the Chino Parts Center DC microgrid project in conjunction with our partner Bosch, who's received a California Energy Commission grant to develop and install the system. But basically we have DC solar connected to the building HVAC, the ventilation, the forklift chargers at the site, and the lighting in order to directly consume the power that's generated on the site. And we also have 900 kilowatts of AC connected solar at the site, and that really helps with the energy bill at that site. So the key parts, my presentation, again, we're very excited, and again, thanks for the opportunity to be here. I think zero carbon energy requires large bulk energy storage, and that's a huge opportunity for both the industry but globally. Flexible demand can be met with vehicle grid integration. Electrochemical energy storage includes working with battery installations to support the grid, but also stationary facilities. Chemical energy storage, hydrogen, provides seasonal energy storage and very long duration storage in order to mitigate seasonal effects of renewable energy generation. Working with means of thermal energy storage is important because it decouples electricity generation from the usage. And all of this together will be part of a renewable energy future, and Honda wants to be at the part of it. So thank you very much.
Ryan, thank you. All righty. We will move on to our final presentation on this panel, and then we'll do some Q&A. So, Roger, thank you for joining us today.
Hello. I feel like I know all of you. I've observed 5 days over the internet of this conference.
God bless you. Yeah, thank you.
So I've been here virtually. And this is also home territory for me. I, over the years, garnered 3 degrees from Ohio State University. So it feels good to be back here.
So if we say OH, you know what to do naturally. You're supposed to say IO, right? All right, keep going. I'm getting too silly in the final hours here.
Well, I'm here to tell you about the Athens pilot microgrid project. It's a collaboration between the nonprofit I head, which is the Center for the Creation of Cooperation, and the Mechanical Engineering Department at Ohio University. Professor Greg Kramer and I are co-directors of the project, and the Sugarbush Foundation has funded it. Somewhere there's a clicker. Oh, there's the clicker.
Oh, I'm sorry.
Mobile clicker. This project started about 4 years ago, and it grew out of the realization that in Appalachian, Ohio, many rooftops don't lend themselves to solar installation. They're oriented the wrong way, they're shaded, they're in disrepair, they're in rented houses. Far less than 50% of rooftops actually lend themselves to solar. So we also realized that in rural areas, houses tend to form small clusters, and often near a cluster of houses, there's one or more ideal location for installing solar that could serve the cluster. And so our idea of building small microgrids was born. Here's an example of 3 houses that it's in a Google map. They're all partially or completely shaded when the trees are fully out. However, there's a small meadow lying between them, which proved to be an ideal location where we subsequently installed a small solar installation to serve all three. We started by soliciting some potential sites, and we went to a local renewable energy consumer co-op and asked them to help us find some sites. We found that there are many, many sites in our area that have small clusters of houses with the kinds of roof conditions I described, and that we're interested in being test sites. Here's an example of one. We drew maps using Google Map to get the orientation, and we worked with an engineering student from Ohio University who did detailed analyses of what sort of solar installation would be needed for that particular site, the costing, and really gave us a sound analytic basis for viewing these sites. As we proceeded, we got more and more interested in storage, and so began to explore that. And we found that there were others in our area also interested in storage. We quickly found that a sort of informal learning community arose around our project, and one of those members had already installed a battery bank of saltwater batteries, which is pictured here. They're produced by the Aquion company. It was partially funded by Bill Gates and a number of other people. It's gone through some rocky times. About half a year ago, had to file for bankruptcy, but was reorganized, and I saw just yesterday it has emerged from bankruptcy. And so these very interesting saltwater batteries are going to be available once more. Another member of our small learning community has garnered Second Life batteries from the airline industry. These are lead-acid batteries that have flown in planes for a limited amount of time and are pulled out with still 70 or 80% capacity, but they no longer meet the rigid standards of the airline industry. And so they're available as Second Life batteries that can be installed. He's installed about 60 of these in conjunction with his solar installation. We also started exploring very early on a bidirectional inverter called the Hart transverter. And it suggested to us the possibility of being able to harvest solar energy and store it and then sell it into the grid to serve ancillary functions. And you've heard some about larger installations that are now currently serving those ancillary functions. It really opened our eyes to this possibility. However, we're looking at a much smaller scale. And in fact, that smaller scale is reflected in the terminology that has started being used in the industry in the past couple of years, as very tiny grids such as ours are starting to be called nanogrids. And in fact, there were articles like one in Utility Dive that came out with the interesting title, "Honey, I Shrunk the Grid, the Emergence of Nanogrids, How Solar and Storage are Driving the Rise of Nanogrids." And we recognized that what we were working on are nanogrids, and so have started referring to our project as a nanogrid project. We also discovered a publication of a study by the Rocky Mountain Institute, which is a very good source of information about renewable energy and battery storage and things. And this study charted out the economics of battery energy storage and really detailed this. They outlined 8 significant revenue streams that could be derived from distributed energy resources, both generators and storage. And a number of these have been mentioned, again, in larger contexts in previous presentations here, so I won't go into detail with them. But it really piqued our interest in the notion that if we could couple our solar generation with energy storage, we could actually have revenue streams that could support, to a degree, small rural installations. We developed a decision matrix and some decision criteria and chose from among the half a dozen sites that we had evaluated and decided that we were going to do a comparative study. One site, we would install an experimental installation that pushes the limits a bit for nanogrids, and the other would be a state-of-the-art conventional installation. The conventional one is using alternating current coming out of an inverter and distributing alternating current to all the participants. The new experimental one is looking at, and this is a picture of the state-of-the-art AC installation, which we were able to do earlier this year, and it's now producing power and serving those 3 houses that I showed you in an earlier slide. The experimental nanogrid is going to utilize the 380 volt direct current RE bus standard that has just been developed in the past couple of years. And I noticed that the previous speaker, in telling us about their microgrid project, has a 380 volt DC installation. So I would bet that they are not only using that, but are members of the RE Bus Alliance that is developing this. I got that right, didn't I? It's a very interesting possibility. And we're going to see how it can really fit with very small scale installations as we have in rural nanogrids. During this time, we've been collaborating with the Athens Energy Institute and investigating a number of ways of incorporating storage into nanogrids. One of the interesting avenues, which again has been talked about extensively today, is that of using electric vehicles in conjunction with nanogrids to store and supply power if the appropriate interface is there. We've also discovered that there is a new experimental set of projects that really define what a transactive grid means. One of these is the Brooklyn Microgrid blockchain project. It is up and running, has been for about 1.5 years now, and really implements what a transactive grid operates like. It's being replicated in Australia and replicated on a very large scale in Germany. So we're going ahead. We've installed our comparative nanogrid. We're getting ready to install the experimental one, but our project is really in mid-stride. We really want to incorporate a lot of battery storage, but unless we are of a sufficient scale, we can't really address PJM and their standards. We look to our local utility to really help us create the interface that would allow us to sell our excess power into the grid. And so in conclusion, I'd like to say that we heard your interest in a platform, so we built a platform, and we covered it with solar panels, making it a nanogrid. And you can see the arrow pointing to 2 smart inverters sitting on the platform waiting to be installed, and they're awaiting the appropriate regulatory regime to allow that to happen. Thank you.
Thank you, Roger. Okay, let's go ahead and open up dice for questions. Tom, you want to go first?
Thank you, Mr. Chairman. I applaud all of you for your presentations, and I applaud staff and whoever else was involved in bringing you all before us. It's a, you know, I kind of think this is America, and and it's a nice little, it's a nice touch. I just want to. My question is, you know, what you see as your as you've moved forward in this, and particularly Roger and Don, about what your biggest hurdles are. But I'd also like to hear Ryan also from a more of a corporate standpoint. What was your biggest hurdles in moving forward at this time? And have any of those things, have they gotten any better, or have they gotten any worse as you've moved on, as you've developed this?
Well, is this on? Okay. We found as we moved through the project over the 4 years that there was a lot of interest in what we were doing, and people came forth and shared their experience. However, as we sought to add the storage component to the solar generation, it was moving into new territory. A lot of people in our area already have solar installations, but very few have battery. And so understanding that and understanding how we can not only use it for backup when the grid goes down, but also to serve these ancillary functions is proving to be a very significant challenge. And in fact, in our comparative installation, the people funding that are holding off on installing a substantial battery pack for a nanogrid size until it's clearer what the path forward is. And so we really look to you to help open that door for us.
Our biggest hurdle, again, goes back to just the education part of it, educating our community or educating our village council who makes that decision about what a energy storage system was. They didn't have the concept. They weren't familiar with it. We were the first public power community in the United States to put the two of them together. So it was an all new learning experience for them. You know, what were the dangers of having energy storage? What were the benefits? And as their elected officials, they take those considerations and want to make the best decision for the people. So we just had to keep educating them until they learned what the benefits are. And I think that'll make it easier as we move forward with our second project, that they understand now what that energy storage system is, what it can do for the community. And I think it'll make it easier to implement the second one.
I think there's a lot of challenges to this future that I outlined, right? Cost. It's everything of new technology comes with a cost burden associated with it. And finally, our customer is the only one bringing any money to the table. So that value proposition has to be there for them, where the value of the product that they buy has to exceed the price they pay, which has to exceed our cost of making it. And if anywhere in that equation there's a discontinuity, we don't have a business. And so everything is challenging in that way. For, say, using cars to provide value to the grid, it's access to those value streams. So for example, in California, we can participate in the wholesale market, in real-time market, directly with the California ISO, and get value by rescheduling the load away from high price hours. And there's a mechanism to do that. Up until a couple years ago, that mechanism didn't exist. And so, everyone can think, oh, this would be a great thing, isn't that smart? But you can't actually do it unless there's a mechanism for you to capture and secure that value. And then designing a program where you can get that value to your customers and having the minimum number of barriers in the way of a customer actually adopting it. We see, for example, demand response programs. It's just one form that a customer has to fill out in order to get a couple $100s a year for managing their air conditioner or managing a demand response program using a car. Putting one form in front of a customer can reduce by 90% your take rate on your offer of adopting that program. And so then designing means to communicate to the customers over and over and over again until they finally tell you not to is it's a huge challenge for us. So consumer adoption, cost, and value, I think, are the challenges we see moving forward.
Thank you. I have two questions, one for Roger and Don and one for Ryan. So Roger and Don, I was just curious, so the what did you call it? A nanogrid? Okay, I got to get used to this. Nanogrid, okay. Is a raised platform that you've put the solar panels attached to. Why did you choose to do that as opposed to the way Don's and the Village of Minster has the array located on closer to the land and on the property?
Well, this particular installation, ground installation, was chosen because the buildings involved all were shaded. None of them had rooftops that lended themselves. So it really made sense to do a ground installation, and building a platform like that and using that on the rooftop. We actually have a multi-purpose structure that we've created. And in fact, we're going to have a really dynamite band come out next month to help us inaugurate.
That's what I was
our
wondering, if you
nanogrid.
use it for anything else, because it looks very nice. Okay.
Yes, they're called the Wild Honeybees, and they're going to help us celebrate our installation of a nanogrid.
Okay.
But there are various options. Sometimes you have buildings, sometimes a barn, sometimes another building that would lend its rooftop to the installation, and there are good reasons to utilize that. But when you don't, then finding an open place for a ground mount makes the most sense.
Okay, thank you. Ryan, I was wondering if you could talk a little bit more about the vehicle charging and how that works. So does a customer get an app? How many customers are engaged in doing it?
Yeah.
How does that work? So does the customer have to figure that out? Is that set it and it figures it out for you? Could you kind of give us a little more detail?
Sure. So one of the fun things about driving an electric car is it comes with an app. And this app allows you to start and stop the charge of your car, to look at the state of charge of a car in case you wake up in the morning and think, did I plug my car in? What's it doing? Oh, it's full. Great. So just having that information gives you some more comfort in driving the electric car. One of the, I think a key customer feature of electric cars is you can start the air conditioning remotely from anywhere in the world. You don't need to have line of sight to your car with a typical engine start thing. So you can have air conditioning in the summertime in Ohio, start 15 minutes before you get to your car, and then it's nice and cool when you get into your car and your ice cream doesn't melt. And that's great. So we have an app that does all that. We added a feature on the app to allow customers to create a profile for their home location, profile for work, basically anywhere where they plug in their car. And around that profile, you can set a schedule. I'm at work. I want my car to be fully charged by 5 p.m. So I put that into the app. I'm at home. I want my car to be fully charged by 6 a.m. I put that in the app. Now, typically, customers, when you plug in a car, you don't need it charged immediately. You just need it charged for when you need the car. And we have tremendous flexibility from that. From the data we've seen with people driving these cars, typically people come home from work 5, 6, 7 p.m., they plug it in, and they don't drive it again until 5, 6, 7 the next day. So we've got a 10, 12-hour window to schedule 40 minutes to 2 hours of charging. That's tremendous flexibility in a system. There's no other electrical load I can think of where a customer turns on a switch and they actually don't care about when it actually runs. And so using that flexibility to create a system that can manage renewable energy flows, manage demand charges for a commercial building, manage demand charges for some other building, to use that kind of a flexibility to find whatever the value is for the customer and then exploit it to their benefit is one of the tremendous capabilities of the V1G system. But it all comes from, you need to get information from the car, and typically it's through an app.
Interesting. Thank you.
Not a question, just two comments. First of all, gentlemen, thank you. It's so refreshing to see a local application of what we've been discussing the last several days. It's great. Thank you. And I guess just thinking back a little bit, I think it was Chris this morning when we decided to take a glimpse into Phase 3. He said that maybe we focus less on identifying markets and more on communicating values. And I think, Dawn, you're a great example of that in terms of the adoption of the community based on communicating the value and educating the people associated with the decisions. Thank you.
Thank you. For Don and Roger, again, as Commissioner Friedman mentioned, congratulations, and we're very delighted to have you here, particularly since you're from Ohio and provide good examples of ingenuity and persistence. For Don, what are the financial challenges that you face, or do you face financial challenges? And I really mean, what are the risks going forward? To what extent is the city committed financially to the project? And then I know you had mentioned you wanted to scale up, and you have like another phase or two phases that are on the drawing boards, or at least you're thinking about. To what extent do you face financial risk when you do something like what you're doing that you haven't been able to offload to your partners, or depend on your partners to shield you from, or maybe there isn't any, which would be perfect?
Yeah, actually, there's very little. We have, the village has very little money invested in the whole project. The investor did that for us. We've got some switchgear that our electric department put in, some poles, those type of things. So it's very small on our part, but we're getting the same benefit that we would have if we would have invested in it, in terms of the benefits of the solar, the benefits of the energy storage. And we're trying to duplicate that model as we move forward with the second phase as well.
And is there any external factors that you have to deal with or to take advantage of, which are required to be advantageous for you to get the beneficial results you have? In other words, are you subject to the vagaries of volatility of the wholesale markets at all, or is that something instead that this is a hedge against, as opposed to facing a risk from?
It really is a hedge against that. We've negotiated a price for the solar that is below market rate, that we use as a predictable rate to hedge against any type of market volatility for us.
Oh, and then, Roger, on your side of it, listening and reading along as you were talking, one of the questions that comes to mind to me are the technical issues. I know you mentioned a regulatory issue that you're facing as far as being able to take advantage of the potential of your nanogrid, but as far as on the technical side, using lead acid batteries or salt water batteries, if I got it correctly, are there challenges that you would face to replicating this, just getting the materials, getting the inputs, the actual physical inputs, and then as far as operating it, is that a challenge for the deployment?
Well, Athens County has spawned a whole series of solar installers, a couple of which have expanded to multi-state areas. Third Sun and Dovetail are both substantial companies. We have a number of really competent local installers also in addition to them. And by and large, they all take a great interest in nanogrids. And so the availability of technical assistance on a basic level is really there and forthcoming. Cooperating with the university, of course, has brought some additional technical capacity to bear on this. I'm not sure, was there,
No, I was curious about about the person who runs this nano grid. Is it, if it were in my backyard, I think it would ultimately be me, and is it something that I could do? Or is there, in other words, do you foresee any challenges simply because of perhaps the complexity of keeping it up and running?
well, there is an educational process, but it's something that I've learned and that you could certainly learn. I mean, my background is in education. I'm not an engineer, but I've found my way through these technical details. And we have a number of organizations in Athens County that consider themselves intermediary organizations that stand between the energy industry, the energy transformation, and the possibilities of solar, of electric vehicles, of storage, and they play not only an educational role, but sort of a hand-holding role in helping people make these transitions. But I think that the technical requirements of nanogrids as we're developing them are well within anyone's capacity.
Staff.
Just a question for Don. Do the monetary savings associated with the capacity reductions from the facility, does that flow to the municipality alone? Or you mentioned some of the partners within the city. Is it shared sort of within the project partners?
No, it is all goes to the village itself. The capacity and transmission savings go to the village itself.
Mahila?
Don, this is a question for you. You mentioned on one of your slides that the energy storage saved you the trouble of acquiring reactive power compensation equipment. Could you talk a little bit about that? Where would you offer up this reactive power?
Basically, the Village of Minster has a lot of large industry with a lot of small motors, so we had bad power quality. What we're going to do is put capacitors on our transmission line, our distribution lines, to be able to improve the power quality for those individual businesses, whether that be Dannon or Nedick Minster. So we're actually going to have to put them there. The inverters of the battery and the batteries themselves improve voltage support. They improve the power quality. So by being able to put the batteries in, we were able to avoid spending that cost.
And another quick question, Don. You said that you're looking to add on microgrid capabilities to your existing facility. So what are those capabilities that is lacking in your current facility?
Basically, what we would want to do is add additional storage, solar, additional storage, to the point where we could be able to sustain our electric grid for the entire village for a period of time until one of the transmission lines come up. One of the major problems that we have as a village is the power outages wise is the transmission lines coming into the village. We have problems with those. Those go out for us. They switch us to a different one which doesn't have the quite voltage enough to support all our businesses. So what we want to be able to do is build that microgrid to be able to sustain us for 4 hours, 5 hours, whatever that may be, until that transmission line is put back together and we can go back off of the grid.
Did you want to go? No, go ahead. Okay. Don, I just was curious. You seem very well-versed on the project, and you've done this presentation maybe a few times.
Yes.
So, do you find a lot of villages your size are asking you a lot of questions about this? And do you have any information to share about if we'll be seeing more areas like yours pursuing it?
Yeah, we've had a number of communities, most of them public power provider communities that have expressed interest in knowing what we have done, have come up, give tours, we sat down and talked with them. So hopefully you'll see this develop because I think it is a good business model for a small community to be able to become more resilient, more sustainability for us. So I think you'll see more communities get involved with us.
Good. And Roger, one other question. So there's 3 homes that share in the nanogrid you profiled here. How does the cost work? Do they all put in the same amount? How is that all done? And do they share in the same ways, or?
We get a reading of how much power was generated in each month, and then we did a 25-year cost estimate on depreciating the assets, and so figured a per kilowatt hour basis and charge each of them according to their usage. We have separate meters on each of the houses. It is really a nanogrid. And
So can I ask, are you one of the houses?
yes, I am.
Okay, great. Thank you.
That's super cool.
Very good. I do have some questions, but first, let me echo what some of my fellow commissioners have said. And these were 3 really wonderful presentations, and it's nice to see some real-world applications within the context of what we've been discussing. So thanks to the 3 of you. Really wonderful presentations. Ryan, let me engage you in some Q&A here.
Sure.
And this really surrounds. Look, Honda's a big thinker, and this may seem like a softball, but it really isn't. And I want to ask you about how you see yourselves in the energy industry. So we've got these very typical, these, at least for us, you've got these very typical what we'll call stakeholders. You've got the distribution utility. You've got folks who are certified as retailers. We're a competitive state. You have the RTO, and you've got various stakeholders outside of those players pushing for their various bases, whether it's a industrial trade association or consumers council. Where does Honda see itself in the space? Because I guess the reason why I ask is I'd imagine that you are a manufacturing company that has now taken a deep dive into the home of customers, and I don't think you're the only one. You may you're certainly not the only sort of technology-based entity that is doing this. And so, how long-term vision? How does Honda see itself operating in the space?
That's a really good question. I think to be successful, I think any company needs to be able to partner quickly, partner well, adapt to fast-changing regulatory structures in order to seek and find value for their customers. And the magnitude of change that the auto industry is going through now and will go through in the next 10 or 15 years, I think is going to be staggering for all auto companies around the world. The magnitude of change in the electric utility industry to adapt to carbon regulations, be they now current and future, it's also going to be staggering. The ability then for us to remake our business in a way that it reflects our current business, which is manufacturing products that we think our customers will like at a good price that they'll like them, involves completely new business models that like we're just frankly experimenting with now and trying to get our heads around and trying to understand. And this application of what we call V1G, just controlling the charge, is really our first foray into that kind of a bold future of creating value through energy management. And if we can succeed in this vision and engage with our customers and get them to adopt that as a part of the product experience of a new electric vehicle, then our product is more competitive in the market, and we can be stand a higher likelihood of success of coming out on top of this revolution.
Very good. Now, with respect to specifically the EV space that you're operating in, the sale of the automobile itself is the gateway for you into the data that you obtain, and then from, I realize this is somewhat in its infancy, but the
Yeah.
data that you obtain that you're then able to do DR and then sell into the wholesale space. And
Right.
So, so well, let me first ask this. So when assumedly when customers buy these cars from you and they opt into the program?
Yes.
Or,
Yeah,
okay.
we envision it as an opt-in. I think one of the risks to us, frankly, is if the customer buys an electric vehicle charging station that's linked to their utility, that's directly under control, they'll come out and their car won't be charged, and they won't know why. And they'll look at that big H on the hood of the car. They don't know that there was a demand response event, that they got a good deal on an EVSE because it was subsidized by a utility or some program. But if the automaker and the customer don't have, if we're not operating in lockstep, we don't know why their car didn't charge, but they'll still blame the big H on the hood for the reason why they can't get to work the next day. So we have to be involved in that relationship in this world of demand response, and we know that demand response is going to be part of the utility industry, and an electric car represents about 3 residential houses of load when it's charging. 6.5 kilowatts it's a big load. That's very important to the utilities, and they want to be able to manage and control those loads. But if our customer somehow gets out of the loop of that control, then their transportation utility is at risk. And as the automaker, we can't let that happen. So we need to be in that loop.
Okay, so for your particular project, conceivably something that could be a hurdle for your project is if the EV charging station in itself is owned and controlled by the distribution utility.
Yeah, that's difficult for us. It would be better to coordinate and have one place for the utility to send, like if they need demand response, they should be able to send it to what we call, say, like a central server. And I didn't talk about this in my presentation, but Honda and BMW and Ford and GM are all working together to create an open vehicle grid integration platform where any utility can work with us to send their signals and have them executed by the vehicle with the customer's input. And that way, if we have 10 cars and the utility only needs 8 cars worth of control, we can pick the 8 customers to make that request.
Yeah.
And then it's all done based on the customer's preferences and schedules. But if the utility just shuts off 10 EVSEs, somebody's probably not going to get the charge that they needed and expected. And for these products to be successful in the market, we don't want a lot of red flag and hesitations from people trying to buy them. We don't want stories about people not being able to get to work because they didn't get the charge they needed.
Yeah, let me play devil's advocate on that. And so if we are indeed going to see a number of new electric vehicles on the road, then Honda may have a program and Ford may have a program.
Right.
And so do you think then from just purely a DR perspective, you'll have the scale in order to actually make a dent if you're called upon?
I think that's the reason for aggregation and working together is that then all the automakers together will have the scale, and we are working together
Okay.
on that backside. We don't want that future of disaggregated effort. We want to be able to compete on the customer side of it and be able to get the most value for our customer, but from the pure say demand response or load scheduling, it needs to be a coordinated effort with all automakers. And a couple of us, I think, are ahead on thinking about this and developing the system. But it's got to be so easy to the customer, right? Especially when we get to a future of bidirectional power flow, V2G. It's got to be as easy as connecting a new computer to the internet, where You can just buy it and open it up and connect to Wi-Fi, and you're in. You don't have to get an interconnection agreement with an internet, service provider in order to get online.
What's
and,
the, got it.
So
What-
in that future.
So what, outside of the charging station, so obviously, so you sell the car,
Yep.
and then the charging station is installed, whether it's through you or a vendor or whomever. What else in the household is needed in order for the customer to be able to use the app, and then for you to be able to aggregate
That's it.
That's it.
That's it. In the household. On the utility side, obviously, we have to have a communication network to back to the utility in order to get whatever signal they're going to react to. But if the customer can access the app, in some cases, the HMI is inside the car. People can input their preferences in the car, and then those preferences are executed. But from a customer buying and installing an electric car at their house, they need an EVSE. In some cases, it just comes in the trunk of the car, and they just need access.
So what relationship then do you have to have with the utility for the program?
It's basically and this is a challenge for us, where every utility is different.
Right.
And we'd like to get to a future where everything's the same. But somebody mentioned earlier, across the country, 3,200 some odd utilities. It's going to be a long road to get there.
That is a long road, Ryan.
Yeah.
We know from experience.
Yes.
Yeah.
Key to us is working together and collaborating. And so I mentioned before the open vehicle grid integration platform. AEP is looking at it to participate. Duke Energy and Georgia Power, the California big utilities are all members of this consortium. It's sometimes slow working in concert with lots of other people, but what's going to be created out of it will be great for all of us.
Okay, last question, and it's something outside of this program that you guys have developed, which is if it's Honda's, again, Honda's a big thinker, and so if it's your desire to not only play in the vehicle space, but in other spaces as it pertains to home energy or small business or manufacturer. Do you envision the model being push a product and then obtain data, or is there a model that you're contemplating whereby and you specifically didn't mention that the home needed a smart meter for your charging station piece,
Right.
a smart meter with whatever other technical capabilities are necessary.
Right.
Is it part of the thought process though that you would so if it's not a product, then you need data, right? And
Yeah.
so this
Data
gets
and control.
yeah, so this gets to the question of, we have our typical stakeholders, and what you're doing right now represents something a little different than
It's
what
completely different.
Yeah, a little different than what we've
Yeah.
seen, and so we've been having this constant dialogue associated with data, and so. I mean, what would be the vision there? I mean, for if you're trying to provide X service or X opportunity to an Ohioan,
Right.
what is your vision of how to obtain the data necessary to do that?
Well, we can get data directly from the cars, and actually the customer doesn't even need to have an app. Vehicles have what's called a telematics control unit on board that will send back diagnostic data and telematics data from the cars, and so that exists today.
Yeah,
even-
but you don't at least right now, you don't envision a space whereby you're not selling a vehicle. Like, you just want to operate in the energy space.
the
You
Honda
want-
Integrated Energy Company, we've not considered those businesses yet.
Okay, gotcha. All right, very good. Fascinating. Fascinating. Thank you very much to this panel. We really appreciate your attendance and your presentations. Thank you.
Thank you.